born some 24 years ago as a fork of NetBSD. And we're currently running OpenBSD 6.6. And the operating system's hallmarks are easy installation, quick installation, rich set of documentation, and very, very good security features. What about security mitigations? Our next speaker, Steen, is going to have a very close and systematic look at them. Steen?
So good morning, everyone. I'm Steen, and today we're going to talk about evaluating OpenBSD's mitigations. So I'm going to explain you why I'm here on stage, and then together we're going to go to an arbitrary subset of OpenBSD's mitigations, and at the end, as usual, with talks, there is a conclusion. So why am I even here? Because like every good computer-related stories, it starts on IRC. We were discussing with a couple of friends the exploitation of a particular vulnerability. And at some point, someone said, whenever I read RobChain, I'm reminded why I run OpenBSD. I didn't know much about OpenBSD. It was like, why? Because OpenBSD is taking security seriously. Wow, that's a short statement. So I did what everybody else would have done. I spent dozens of hours reading OpenBSD source code, mailing lists, design documents, PDF, and everything. And then I rented back on IRC. And another friend said, hey, you should do a talk at the CCC about this. It's a good idea. It's never going to be accepted anyway, so why not? So here I am. Yeah. So OpenBSD, it's an operating system, for example, like Windows or Linux kind of things, except it's based on NetBSD. It was forked by Theo de Rad in October 1995. The goals taken from the goals.html webpage of his website is to pay attention to security problems, fix them before anybody else does, and to be the #1 most secure operating system. That's really cool. Also be politics-free as possible. Solutions would be decided on the basis of technical merit. I really like this. That's nice. People had low expectation for my talk. Things like misinformation, low-quality talk, false assumption, international embarrassment, apparently. So we'll try to disappoint these people. More seriously, when the abstract of the talk was published on the C36C3 website, there were a lot of heated responses. Like, just look at the innovation webpage, just look at the events webpage, there are a lot of mitigations. How dare you say that OpenBSD is not secure? That's the point of my talk, actually. OpenBSD has a lot of mitigations, but I want to know if they are working or not. Having a list is not enough. Also, there are almost no exploits for OpenBSD. Well, there are no exploits for TempleOS or Haiku or MenuOS, but I'm not sure they are super secure. Also, OpenSSH and OpenSMTPD are really great. I know, I'm using them. This talk is not about OpenBSD software, it's about OpenBSD security mitigations. Someone else said that all the mitigations are complementary. Why are you nitpicking on small mitigations? They're just a hand-wavy statement. Like, everything is complementary, don't you dare criticizing OpenBSD. Someone else said just read undeadly.org, which is a website dedicated to news about OpenBSD. But on undeadly.org, every time there is a new mitigation, everybody is cheering at it, but I haven't seen anyone criticizing the mitigation, saying there is a weakness here, or maybe this, or maybe that. And also, when I was discussing with friends that are writing exploits, they are complaining about people fuzzing OpenBSD, not about new mitigations. Also, someone said that the title is clickbait, but apparently it's not clickbait enough because the room isn't full. So security mitigation, how do we measure security? It's really hard. Alva Flate designed the mitigator creator, which is an alligator always working to make exploitation harder. Like, yes, I killed his vulnerability, but it's not really helping. So how do you measure a good mitigations? How do you design good mitigations? Halvar also wrote on Twitter, because apparently he disliked writing blog posts for some reasons. Said that to have a good mitigation, you should avoid hand-wavy statements like, it makes harder for an attacker to do that. You should have stuff like, what class of bugs does it kill? Or what CV, like, this is killing CV 1, 2, 3, 4, for example. Or by how many hours does it delay the publication of a working exploit, for example. Because it makes harder for an attacker. It's not something that would be acceptable, for example, when designing cryptographic protocol or a security protocol, like, yes, I added a for loop here because it makes harder for an attacker to get a clear text. It doesn't work as well. Also, for a good mitigation, you should ask your friendly neighborhood exploit writers about this. Like, hey, I've wrote these mitigations, it's killing this class of bugs, here are old exploit. Can you bypass it, please? Can you try? And also, code review. Where is the mitigation coming from? Did you read some papers? Or did you come up with the idea yourself? Other people are using it, maybe? What is the code complexity? So it doesn't guarantee good mitigation, but at least I think that good mitigation stems from these good practices. Also, threat modeling, I think this is really important. Someone called Ryan Mallon said, threat modeling rules of thumb. If you don't explain exactly what you are securing against and how you're secure against, the answer can be assumed to be bears and not very well. So for example, there was a mitigation added to OpenBSD, and the commit said, I quote, thereby forcing the attacker to deal with the hopefully more complex effort of something. This is not something you want to read in a changelog for adding a new mitigation. So here we go. In this talk, as I said, I'm going to go with you through a subset, an arbitrary one of OpenBSD's mitigations, where they're coming from, where they're invented by OpenBSD or improved by OpenBSD, maybe. What are they defending against? Are they effective? Are they killing exploits? And how is the outside world doing compared to OpenBSD? For example, Linux has been not really improving, but Windows has been investing a lot of money and effort and time into making it more secure. Why an arbitrary subset? Because I only got 45 minutes and a bunch of questions, so that's not enough time to go through every single one of them. There are not a lot of sources in my slides because I don't have much space. Well, it's a big screen, but still. But there will be a website at the end with all my research material published there. I also put small pufferfishes in the bottom of the slides as a notation mechanism to express my opinions about the mitigations. So yeah, here we go. Attack surface reduction. Ivan Fratik, which is someone working for Google's Project Zero, said in 2019 that empirical evidence suggests that attack surface reduction is one of the most impactful things that can be done for product security. So this is a class of mitigations that should be really effective. Privilege separation, privilege drop. In 1997, a long time ago, Daniel Bernstein wrote Qmail, and Qmail was composed of several processes with only one running as root. So as an attacker, if you manage to compromise, for example, a process talking to the internet, maybe it's running with low privileges, so it wouldn't yield you automatically a root shell. That's really good. Postfix did the same year, and 5 years later, OpenSSH got privilege separation. So if you have a remote code execution OpenSSH, maybe it doesn't give you a root shell automatically. That's pretty cool. Almost all OpenBSD written programs nowadays are using privilege separation and privilege drop. Privilege separation is to have different processes running with different privileges, and privilege drop is the idea of dropping your privileges as soon as you don't need them anymore. For example, when you are issuing a ping command on Linux, maybe on OpenBSD too, I don't know, ping is set to ID because it needs to have high privileges to open a specific socket, and then it immediately drops privileges to send the payload. So that's the idea of privilege drop. OpenBSD is using it almost everywhere, I said there. That's why I put 5 pufferfishes. It's a really good unit, I think. For example, they've got rootless Xorg since 2014. That's really amazing, but they kept it set to ID. So this resulted in a trivial local root on OpenBSD. Okay, that's just me being mean. Pledge. I really like this one. So in the Linux world, there's something called seccomp that was created in 2002 and merged in 2005. The idea is that the process could enter a mode of secure computation in which only the exit, sig return, syscall are allowed, as well as read and write on already open file descriptor. That's not really convenient for real-world programs. So seccomp BPF was created in 2012, and with this you can restrict what syscall your program can make, for example. OpenBSD created Tame, which was renamed as Pledge in 2015. And it's a really amazing mitigation. I really like it. It's really simple to use because contrary to seccomp, it's not based on syscalls where you have to dig through your operating system source code saying, what is this syscall doing? Do I really need it for this Java program? Maybe not, I don't know. Here it's capability based. So for example, you can say, hey, this program is only allowed to use standard input, standard output, or this program is allowed to do DNS resolution, and that's it. For example, I think the NTP client of OpenBSD is running different processes with different pledge policies. Like one is allowed to resolve the domain, the other one, more privileged, is allowed to change the time of the system, for example. That's really neat. Also, it's more used than seccomp. Seccomp is mostly used like in Docker, for example, or Tor IPT at some point as well, a couple of other programs, Chrome maybe. But in OpenBSD, there are 850 calls to pledge in OpenBSD SRC, so it's used a lot in OpenBSD's code base, and I think it's really impressive engineering work, and it's working very well. Super effective. They've got Unveil, which is kind of pledge, but for files. Not really. The idea is that pledge allows you to restrict the view of your file system to a specific program. For example, if you've got a web browser, the web browser needs to be aware only of, for example, a folder for the cache and the cookies, and another one for downloads, and that's it. The web browser shouldn't have access to your SSH keys, for example. It doesn't abort on violation, so if your program is behaving weirdly, like trying to access your SSH key, maybe you will get a log message, but the program won't be aborted automatically. It's used by 77 userland program, OpenBSD. That's kind of a decent number because OpenBSD, with its default install, doesn't come with a lot of programs. I think that this one is also really good. It's like AppArmor or SC Linux running on Debian, Ubuntu, or Android, for example. But I think it's much better because the policy is residing inside of the program. So let's say you're using wget to upload some file on the internet. You can make the whole file system read-only because wget only needs to read some file on your disk and then upload it to the internet. Or if you're downloading a picture, the only thing that needs to be writable on your disk is the destination file for the picture you're downloading. You cannot have that with AppArmor, which is more like, yeah, wget can only access this and that's it. So being able to reduce the attack surface depending on what your program is doing, I think is really cool. Hardware vulnerability, we got a lot of them in the last 2 years. Apparently, you cannot trust your CPU anymore. That's a shame. Here, I think the most interesting thing that I'm going to talk about is the reaction time, because it's usually faster to update your operating system than it is to update your CPU. And for some vulnerabilities, when they were published, researchers managed to write proof of concept in a matter of hours. So I'm quite sure that serious players are able to have production-grade exploits in a couple of weeks, maybe months. Hyper-threading. So OpenBSD disabled hyper-threading support by default, which is a bold move, and a lot of people call their names because of this, like OpenBSD doesn't care about performance, blah, blah, blah. But they did some benchmark, and the performance impact is pretty low, except from some specific workload. And this allowed them to dodge a couple of vulnerability, for example, Lift in userland, or MDS in its variants like zombie load or Riddle, for example, also as userland. So this maybe should have been in the attack surface reduction part instead of here. I think it's really cool. It's a really bold move, and I think it's a good indicator that there are some people at OpenBSD that care about security. Spectre v123. The idea of Spectre is that the branch prediction speculative execution of your CPU has observable side effect. Like your CPU tries to be smart and infer some things, and an attacker can observe the CPU doing this and extract some data from this. So Spectre v1, which is the first variant of the Spectre attack, the mitigations on Windows is compiler-based. On Linux, it's manually removing some gadgets using a magic grep. And OpenBSD, there is nothing, so you need to update your CPU if you're worried about this. Spectre v2, also compiler-based on red pollins. Day 0 for everyone, that's really impressive. 3 months for AMD64 on OpenBSD. That's not a long-ish time, it's all right. KPTY, also Spectre v3. Kernel page table isolations. Day 0 for everyone, 1 month for AMD64. That's pretty fast. Interestingly, and because I'm a mean person, OpenBSD got KPTY after Dragonfly BSD, NetBSD, and FreeBSD. That's just me being mean. There are other ones, Lift, MDS, SwapArgs. Everybody was using the same mitigations, except that OpenBSD was able to dodge a couple of them for userland because they disabled hyperthreading. That's really cool. So everybody pretty much the first week, day 0, day 3, 9. Yeah, that's really good. And for Lyft, interestingly, 9 days after the embargo was lifted, Theodorad said that there won't be any mitigations for OpenBSD 6.2 and 6.3 despite them still being supported at the time, which is an interesting statement. He sent this on the mailing list. I'm not sure if people know about it. Randomization. OpenBSD has a really strong focus on randomizing everything to make the life of an attacker harder. ASLR. So the idea of ASLR is to map area of the hazard space at random location. For example, your stack is the random location every time your program starts, so is your heaps, your libraries, and everything. It was invented by the PAX project, which is the patch for Linux in 2001. And the same year, OpenBSD did a random offset for the stack. That's pretty fast, pretty neat. 2003, OpenBSD did a random offset as well for libraries and mmap. And it took 2 more years to Linux to join the bandwagon. Technically, it's ASR and not ASLR for OpenBSD because the delta between the different maps is constant between the launch. For example, when you're running your binary the first time, you've got the delta between your, your library and your stack, for example. And when you relaunch it, they are mapped at different offsets, but the delta is still the same. It doesn't matter that much, at least still better than per boot randomization like Android, iOS, and Windows are doing. Also, OpenBSD claimed to be the first widely used operating system to have ASLR, but there was Gentoo Arden before and Adamantix. I don't know if Gentoo Arden was more popular than OpenBSD because they don't publish numbers, but I think, I'm not sure the statement is true for OpenBSD. Position-independent code. So here it's not only the stack, the heap, and the library that are mapped at a random offset, but every time you're running a program, the binary will be mapped at a random offset, removing fixed point for the attacker to see where it is or what to overwrite or where to jump, these kind of things. Also invented by PAX, 2001. Gentoo Arden enabled this for the whole userland in 2003, and Fedora and Red Hat Enterprise Linux used this for security and network-facing binary because there were some performance concerns to enable this mitigation. OpenBSD got support for Pi 5 years afterwards. 2011, Pi by default on iOS and OS X by Apple. There are a lot of text in this slide because I think that here the timeline matters. Also 2012, Android, that's really cool. And 2012, Pi enabled by default on OpenBSD. That's pretty nice. Except that on the OpenBSD's website, it's written that OpenBSD 5.3 was the first widely used operating system to enable it globally by default on 7 hardware platforms. Android was first for 6 different architectures. Fedora was first for 8 different architectures. And also there was Gentoo Arden, Adamantix. Maybe they got less users than OpenBSD at the time. But also Apple enabled it for OS X and iOS. And I'm quite sure this is more mainstream operating system than OpenBSD is. So it's still an amazing mitigation. Carl, I really like this one as well. So July 2017, OpenBSD relinks kernel object at a random after every boot. Like the kernel is linked, like if your kernel was a giant puzzle, the pieces would be shuffled and assembled in a different order after every boot. So when you reboot, your kernel looks entirely the same. And for example, on Ubuntu, every time you're rebooting, the kernel is the same. So as an attacker, I only have to have the same version of Ubuntu as yours, write my exploit for the kernel, it works. It will work usually on your machine. So it's pretty nice. It kills single pointer leaks and relative overwrites, because if I can leak a pointer to your kernel, I know where the pointer is, but since the kernel changes upon every boot, it doesn't give me much information. And also relative overwrite, if I'm able to write whatever I want, but in a relative manner, I don't know what I'm going to overwrite. It's really useful against attackers that doesn't have an arbitrary read or a CPU side channels. So yeah. Also, the debuggability of this is really horrible because everybody has a different kernel. So if my OpenBSD crashes and I want to send you the stack trace, I will have a different one that you do, for example. Or maybe I'm not a power user, I don't know much about this, so I'm just sending you a screenshot, and there is no way for you to know what my kernel layout is looking like. Also, it doesn't work very well with trusted boot, because you've got a different kernel after every reboot, and you would have to sign it every time. It would kind of defeat the purpose of trusted boot. But OpenBSD, I think, doesn't really care about trusted boot, so it's all right. This one is interesting as well. They are randomizing like they do for the kernel, except for the libc and libcrypto at boot time. That's pretty nice, 2016. It also kills single pointer leak and relative overwrite. If an attacker has an arbitrary read, this mitigation is moot. And also, this one is vulnerable to blind drop, but OpenBSD has some measure in place to make blind drop a bit more difficult. It's useful against remote attacker, but since it's per boot, it's entirely usually useless against local attackers. Library order randomization. So here is not randomization inside of libraries, but the library are mapped in a different order every time. 2003. This was also done by Android at some point by default. It's a smallish improvement over ASLR, but when you've got a single leak to a library large enough, for example, the libc or the libcrypto, I don't know, there are usually enough gadgets there that you don't need to look for other libraries. Also, the entropy is pretty terrible, because an attacker, I don't care about figuring the particular order of all the libraries. I only need my libc to be the first one, for example. So if I've got n libraries mapped, I've got one chance out of n to exactly hit this library the first try. So it doesn't hurt to have this, but it's not very effective. WX, this mitigation idea is to have the memory section either writable or executable, but never at the same time. It's a pretty old mitigation. It was, I think, first made public by Casper Dick for Solaris in 1990 something. Solar Designer wrote a patch for Linux kernel for this as well. It prevents the introduction of new code, because an attacker cannot put his code into a writable section, directly jump onto it. This used to be the case in the 90s, but nobody is doing this anymore because of these mitigations. OpenBSD was pretty late to the party. It took them a couple of years, 2002 for user land, 2015 for kernel land. Amazing mitigations, except that it's lacking things like PAX mprotect from PAX and NetBSD nowadays, I think, or ACG on Windows, or the kinda hardware equivalent in Apple world, which is KTR in hardware. The idea of this is that the operating system will keep track of the memory allocation. For example, if you are locating a page as writable, it can ever be mapped as executable. Even if you map it as prot known, for example, and then map it as executable. And this really prevents the introduction of new arbitrary code, because otherwise an attacker, if I've got, I don't know, some ROP gadgets and I've got code execution, what I can do is that I can allocate a section of memory, mark it as writable, put my payload there, map it as prot known, and then map it as executable and jump on it. So this is basically the attacker adding new code inside of the binary. And when you've got mprotect, PAX mprotect kind of things, you're not allowed to do that. So you have to write your whole payload in ROP or use data-only attacks, but you cannot bring your own shellcode anymore. WX refinement in 2019. So Theo said that he wanted to block direct syscalls from this area, forcing the attacker to deal with the hopefully more complex effort of using JIT, or probably even harder, discovering the syscall stub directly inside randomly relinked libc. What is the point of this? That's a subset of PAX mprotect that I mentioned previously. They are blocking syscall from executable memory. So if an attacker has an executable memory, he cannot issue syscalls from here. And the further refinement was to block syscall from memory that doesn't have the msyscall flag. So the operating system will map a particular section of your address space when your binary is running, and you can only issue syscalls from this version of the binary. Couple of days ago, Samuel Gross did a talk about iMessage exploitation, and this exploit would have entirely bypassed this mitigation, and it's not even present on Android, because when, as an attacker, you've got enough control to map an area as writable, put your code there, map it as executable, and then jump on it and then do a syscall, usually you've got enough control to just rope your way to syscall stub wherever they are, because you usually have an arbitrary read anyway. This mitigation is pretty useless. I think this is the juicy part of the talk. It's about other memory corruption mitigations. Userland heap management, July 2008, Automalloc by Otto Merbig, I think, sorry for butchering your name. And Damian Miller is an amazing piece of software. Out-of-band metadata, so when your allocator is allocating some stuff, the metadata about the data that was allocated are kept separately. So as an attacker, if you've got an overflow, for example, you're not able to mess with the data that are here. Also read-only structures, so as an attacker, if I've got an arbitrary read and arbitrary write, for example, there are some structures that I cannot mess with. Quarantine with delayed free, the idea is that once your program doesn't need the memory anymore, maybe you want to free it, but the free doesn't happen immediately. The section will be put into quarantine, at some point will be freed. This helps to mitigate use after free, because as an attacker, it's a bit harder to know when the memory will be freed. Junking, like when some memory is allocated, there are junk that are put there. So as an attacker, if I try to immediately look into this memory, I'm not able to leak some things. Canaries to detect linear overflows or linear underflows. There is a secret value that's put behind or before the buffer, and when an attacker, when I overflow it, the program will notice at some point that the canary value has changed. Quad pages, page alignment, the idea is to align your allocation per pages. So as an attacker, when I've got an overflow, odds are that I will fall into a page that is not mapped. Guard pages like canaries, but instead of putting secret values, you're putting entire pages before and after, map them at prot known, for example. So when the attacker touches them, everything will explode. As usual with OpenBSD, everything is randomized everywhere. It's a really cool piece of software. Unfortunately, it's a bit slow compared to, for example, Scudo, which is the Google hardened allocator that they plan to use for Android. Some benchmark shows that Automalloc is 12 times slower, but apparently the OpenBSD people care more about security than care about performance, and that's entirely fine. Read-only relocation. This one is more tricky to explain, but basically the idea is that when your program needs a function from another library, like let's say you want to display some text, you use printf, and your binary doesn't implement printf. So it will ask you, hey, where is the function printf again? And there is a small stub that will say, oh, let me look, here it is, there you go, and the program will take the function, put it in a small cache, so next time it needs to call printf, you can just look in the cache and call printf. The idea of read-only relocation was created by Red Hat is that to make this cache as read-only. Because an attacker, for example, if the cache is not made read-only, what I can do is that I can swap the pointers there. For example, next time you're going to call printf, since I messed with the cache, you're going to call system and give me a shell. So the idea is to have this as read-only. But the caveat is that you need, when you're starting your program, to resolve everything, because you cannot dynamically change the cache. But there is a plot twist. OpenBSD still has lazy bindings, which means that they're resolving things at runtime, but still having a read-only zone. This is a bit weird. But so the way they are doing this is by adding a new syscall called kbind. And the idea of kbind is that it allows the program to have an arbitrary write inside every memory that is mapped in the address space. So even if it's read-only, the program can still write there. So to prevent an attacker from using it, there is a call side verification. Like the first time it's called, the operating system will remember where the function was called, and also use a magical cookie to make sure then the caller knows the magical value to be able to use it. Unfortunately, you can just rope your way to bypass the call side verification, and also the cookie value when you've got an arbitrary read, it's really moot. So I think this is a dangerous syscall, and the right way would have been to have immediate bindings instead of still supporting lazy bindings, which are things from the past. Trap sled. This one is hilarious. So Todd Mortimer sent a patch to replace the padding between functions that used to be NOPs by traps. And the idea is to remove NOP sleds from program libraries and makes it harder for an attacker to hit any ROP gadget or other instructions after a NOP sled. Nobody is using NOP sled with ROP. NOP sled were used back in the day when the stack was executable. People are jumping precisely to the gadgets nowadays. You can look at every exploit out in the wild. Nobody is using NOP sleds. Also, Microsoft Visual Studio had these features since the 2010 editions and never branded it to the security features. Also, OpenBSD has an obsession about removing ROP gadgets. They're doing this by changing the register selection algorithm. Like instead of using EAX, for example, they were favor EBX instead. Why not? They're also replacing instructions. So instead of moving A to alpha, they are exchanging A and B and then moving and then changing again. They are forcing alignment with the trap sled. There is a whole jump above a trap sled at the ret instruction to prevent an attacker from jumping in the middle of an instruction and hitting the ret afterwards. Also, they've got red guard to protect against aligned ret usage, but I'm going to discuss red guard a bit more after. ROP gadgets removal. Why? Why would you do this? Because they are using a script called robgadget.py, which was written by Jonathan Salwan. It was written as a proof of concept for fun. Nobody is using it except maybe during CTF as a try, and usually it doesn't work because the heuristic it's using are pretty simple. And the way they are measuring the success is that they're running ROP gadgets on a kernel binary to generate a userland execv ROP chain. And the ROP gadgets, the PY script, managed to generate a full chain before their mitigations. And when they apply the mitigations, ROP gadget doesn't manage to generate the complete chain anymore. That's a weird metric. Also, apparently, all their dents to remove gadgets are reducing the number to 11% on MD64. That's not a lot. When you're writing a ROP chain, usually you need like, I don't know, a dozen gadgets, maybe 20, but not that much. And 11%, this doesn't make any difference. Like there are still dozens of hundreds of gadgets lying around. They claim that there are no more ROP gadgets on AM64. That's amazing. So I've run robgadgets.py on the kernel binary and remove all the ret-based gadgets, and there are still 12,891 drop or co-op or pickup gadgets everywhere. Also, it doesn't kill, as I mentioned, ROP, co-op, pickup, and all the return to CSU, return to lib, return to anything. And Theo said that once they address the ret problems, everything else would be easy to address. And also, any case, substantial reduction of gadgets is powerful, except it's not. There was a paper published in 2019 by Michael Brown and Santosh Pade called "Is Less Really More?" that is explaining why removing ROP gadget doesn't usually improve security and sometimes even worsen it. Amusingly, GCC used to have an option called -- and mitigate ROP, but it's now removed because, I quote, "This option is fairly ineffective. Nobody seems interested to improve it. Deprecate the option so it won't lure developers to the land of false security." Red Guard. So Crispin Cowan and his friends wrote StackGuard 1997. The idea, as mentioned previously with cookies, is to have a secret value somewhere. And when the attacker tries to override things to memory, the attacker will also override the cookie value, thus allowing the program to detect that something is wrong. Here, it's usually on the stack. Like when you're calling a function, the return address, because you're executing your program, at some point you might want to call a function, for example, but you need to know where to come back. So the idea is that when you're calling a function, usually, or at least on MD64, you're putting the return address on the stack, the function is doing things, and then it's taking the address back and coming to the call site. So as an attacker, if I can overwrite this address, I can make the control flow of the program point wherever I want. OpenBSD added stack cookies in userland in kernelland in 2003, 6 years after the invention. And amusingly, they were using a segment filled with random data for this. And they marked it as static const. So the compiler was smart enough to say, this is a static const segment, so it must be 0. So it simplified the comparison for cookies. So the cookies on OpenBSD were ineffective between 2016 and 2017. So WordGuard 2017 edition, the idea was to XOR do an exclusive OR on the return address at top of the stack.